Hello. Hello and welcome to the first of our student talks. Today we'll be having a talk by Ethan, and this is following the differential geometry talks given by Professor Joseph Muscat. There will be a second student talk where we'll be having two talks, hopefully, and that will be in a week's time. So hopefully we'll see you there. All right?
Thank you. So hello, welcome. So I'm Ethan. I'm a fourth year here at the university, and my area of study right now is theories of gravity and stuff. So I've got lots of experience talking about manifolds. So just right. So today I'm going to be talking to you about well. So first I'll give you a little bit of an introduction to vectors, just a bit of a refresher on what Professor Muscat talked about in the last few weeks. I'll then develop the idea of tangent spaces. So that's, you know, tangent vectors and all of that. We'll get to that. The whole idea that while we're here, it's Riemannian manifolds, which are highly important in this field of study. And we'll go on to metrics. We'll talk about the metric tensor and how we can define distance functions and actually get a metric on our Riemannian manifold. I'll talk a little bit about pseudo Riemannian manifolds because they are of utmost importance with special and general relativity, which will be the final few parts of my talk. So just as a little bit of an introduction, reminder to you guys, a manifold is a topological Hausdorff space. Or Hausdorff just means things are close together or whatever. It's dimension n that locally looks like the Euclidean space. So if we remember, we have some manifold. So a manifold, again, topological space, random space. So at every point here, we can define a neighborhood around that point that is homeomorphic. So we can define a function phi, for an example, which is continuous and has an inverse that is continuous, that is homeomorphic to the plane, for an example, if we're talking about two-dimensional manifolds. A little thing to note is that this thing here, this subset of this open subset of the topological space, and along with the mapping, is known as a chart. So it's a chart. And a set of these charts are known as an atlas. So if we can think of, for an example, the Earth, if I want to map out the Earth, I would split the Earth up into the North Pole, the South Pole, and the rest of the Earth, where I'd have like a map for the North Pole like this, map for the South Pole, and then some map that shows the rest of the Earth, right? Because obviously there are problems with the poles when we use regular mappings. So a useful thing I'll be talking about a lot, I'll probably use a lot, is the concept of a scalar field. So scalar fields, what they are is basically they're functions from the manifold or a subset of the manifold onto every single point in space and time. Well, onto the real number. So it basically assigns every point in space and time a real value. So, well, I guess it could be complex, but let's keep it simple. So for an example, we could think about temperature, right? Temperature. If I want to, for an example, take this wall, right? Every point on this wall can be described using r squared. And at every point in this space, I can define a function of the coordinates that gives us a real value that kind of defines the temperature at that point, right? So that's the kind of typical example of a scalar field. Right, yes. Now, scalar fields, of course, they're they're important for many reasons, because like they're not the only type of field that come up in this sort of studies, because of course you can have vector fields, which is at every point in space you can have a vector assigned to that point. You can have at every point in space a tensor assigned to that point. We've talked about tensors now, so we can use those. So yeah, that's the kind of idea that we use here. So to describe a lot of different things. So something that I find rather important is to ask the question about what is a vector. So can someone give me some definition here? Yeah, that's very good. That's probably the rather basic idea of now, like. But here, I'm going to talk a bit more abstractly about vectors. Of course, vectors we can think about, point in space with arrows like that, right? But here I'm going to talk a little bit about vector spaces. So vectors are just elements of vector spaces. And a couple of things I like to discuss a little bit about vectors is, well, of course, they act on functions. Yeah, so like if you recall that a dual space, right? So if I just define here, so the dual space of a vector space is defined as the set of homomorphisms from the vector space to the real line. It's just the set of linear maps from the vector space to the reals. So it's the set of all functions that map a vector to a number. So for an example, I can think of the magnitude, for an example, of the vector is such a function that does this. These all have the special property, have the special linear properties. So if I say psi, for an example, is in home VR, then we get that psi v plus w is psi v plus psi w, and some number alpha times some linear multiple of the vector scales nicely like this, right? Yes, so psi, this set here is the set of psis that map v onto r, right? But that have these two properties. So this has these two properties, right? Specifically, that these are like homomorphisms on vector spaces, is what the words, the technical jargon that we use. Right. Yes. So the point I want to make here is that vectors act on these things, on these functions. So the way we work with these functions, usually we like to think about it is mapping a vector onto the real line, right? Oh, it should be like that, right? Well, in some sense, we can think of the vector itself as the function object, kind of. We can say that if we have this phi, we can act on it using the vector to give us a number, to give us some number in R, so let's say x. So how would I think about this, for an example? Let's give a more concrete example. So if I were to take, for an example, let's take my vector space to be R. So I want to consider the dual space between the reals and the reals, right? I can take a function here, for an example, this function. This function has these properties, and it is an element in our dual space. However, if I take a specific vector in our vector space, let's say this vector here, a random vector, right? I can consider this to be acting on the set of elements here. So on this vector could be acting on this function, right? So we could say it like this. So v, and it will assign this specific number to this function, right? So this kind of idea, we can use it to kind of think of vectors more as things that act on operations, right? Now, just to remind you again, like here we have the component space. So vectors can be written in this sort of components here, where we have our usual basis vectors, depending on the dimension of our vector space. And yeah, and the components of the vector. Something to note, something I like to remember, like these things have jargon, right? They have, what is it, contravariant and covariant, depending on where you want to put the index. The way I like to remember it is covariant is the low one because co is low. It's just a random little thing that I have in my head. Yeah, so that's kind of where this is going. So we can use vectors as functions, and they can be expressed in this sort of form. So where these vectors are acting on these basis vectors. So these vector components are acting on these basis vectors, kind of. So, yes. Okay, yes, I didn't really explain that. You're right. So a vector component. So if we imagine a vector, like, okay, so vectors, as we know, they come with a basis, right? So every vector in the vector space is a linear combination of each component. So if I say, let's take this set E alpha to be our basis, right? So the numbers V1 that multiplies E1 plus V2, a number that multiplies E2, and so on. These numbers here are the components. So in the case, for an example, let's take a more real example, right? We have X, Y, and we have this vector right here, which is 1, 1, right? So it's this vector here. Yes. This we can write it out as I plus J. Yes, where I and J is the unit vector. Like I is this one and J is this one, right? Along the different axes. Now these, of course, they don't need to be constants like they are here, but they are just they are the basis vectors, so to say. So all the components are the coefficients of the coefficients with respect to the basis vector. So it's a set of coefficients that define that vector, so to say, in a specific basis. So in fact, like if you were to change your basis, your components would change. So that's kind of a good point to make. So the next thing I'd like to talk a little bit about is some rates of change, right? So derivatives. So an important thing that we like to define in maths and mathematical physics is the gradient, right? So raise here. So the gradient, all it is the set of partial derivatives of a scalar field. So the gradient of a scalar field, I'd like to say. So it's a set of partial derivatives with respect to the coordinates that you are working in, right? So for an example, if we have some scalar field, let's say, I'm going to work in Cartesian coordinates. Let's say this one right here, x squared plus y squared. We can calculate its partial derivatives like this. It's 2x. And in the case of y, it's 2y. And in the case of z, it's just 0. So we calculate those partial derivatives and we set it into a covector. Now, it's a covector because there's a theorem that says that that it transforms as covectors, and you can prove this rigorously and stuff. I'm just going to put it straight into a covector. So like this. So in this case, grad phi is 2x, 2y, 0. And we can actually just index each one, right? We can say that we can just write this thing here, and we can specify alpha to get one of these. So if I say this is x, for an example, this will just give me 2x. It's a matter of notation, right? But it is just, so what this is what this is describing is, if you have a function, let's take it in Cartesian coordinates just to make it simple. The function the gradient describes the function along each of the three axes, right? And it's kind of gives you a vector of how it's changing overall, a co-vector, so to say. But anyway, why is this useful? There's a lot of reasons, very many reasons. And one of them is this thing right here, the directional derivative. So let's consider the temperature in this room, right? Let's say I want to find out how does the temperature change from one corner of the room at the back there all the way to the corner over here. How would I find that out, right? Well, the answer is, the way we'd like to define it anyways, is, well, this quantity right here, right? So what we do is we act with the vector onto our derivative, onto our gradient, and we multiply each component of the gradient with the related component of the vector and sum. So just a reminder, this is Einstein notation, so top and bottom. If you have repeated indices, you sum over each of the indices. Yeah, so that's great. So if we, one example we can write is, if I want to find the directional derivative of this scalar field along, I don't know, this vector here, let's call this 1, 1 for an example, I just literally carry out this operation. I could call it, I don't know, psi v, for partial v, psi, the derivative of psi with respect to v. And I could take it, well, it would be 2x times 1 plus 2y times 0 plus 0 times 0 times 1, oops, 0 times 0, and you just get 2x plus y plus 2y. Would be how this scalar field would change from along this line. So this would give you some function of some parameter, which would tell you how this changes along this line. So it is literally the derivative in a given direction, right? So is there any questions so far? Is there anything in the chat? Okay. Yeah. Here. Yes. Is that better? Yeah. Thank you.
How you could compute the alphas exactly? What do they exactly do?
Okay, so okay, yes. So the alphas basically, when you have, let's talk 2 dimensions, right? If you have 2 dimensions, you have x and y coordinates. In this case, alpha, okay, this is just a shorthand notation. In reality, like, if I were to use this, where's the eraser? If I were to use this notation, I would label my axes like this: x1, x2. So these are labels, not powers, right? So in this case, like this psi, so yeah, I probably should have made this a bit more clearer. In this case, I could change this to, this function would become x1 squared plus x2 squared, like this, right? And you'd get all of these derivatives, and here you just end up with x1 and x2 like this. So basically, those alphas, they are labels for your coordinates. Because if you have, I don't know, 100 coordinates, for an example, you're not going to come up with a letter for each one. And it's just a lot easier just to number them, and it's a lot easier for notation purposes just to give them like this sort of summation, right? This sort of, this is the Einstein summation convention. So like when we see one on the top, one on the bottom, it means we sum all over all of them. Okay, does that make sense? There. Right, so all of this leads us to the idea of a tangent space. So let me make some space here. So a tangent space, let's, before I start with that, I'll just make it a little simpler here. Let's consider a curve, right? A curve. So let's go, we have our curve in R2. Well, it's going to be, you know, our one-dimensional manifold, but it's represented in 2 dimensions. So we have some curve like this, yeah? Now from your A level, like a lot of you probably remember, if at a point here, for example, I want to find the line that is tangent to that point, we would just take the derivative of that line and of that function and evaluate it at that point. And we would get the gradient of that function, so to say, of that line. And basically, tangent spaces, all they are, especially in this one dimension, is this line, right? A tangent space is just this line for a one-dimensional manifold. A tangent space, strictly speaking, at a point P of a manifold is a vector space of the same dimension of a manifold, which that is a theorem that needs to be proved on its own, but I'm just putting it there. That's defined by the set of tangent vectors to the, of curves passing through the point. So that's the technical definition. Let's explain that. So if we have, for an example, it's very easily seen on a 2 manifold. So if I consider a 2 manifold like this, and we get a point P, right? If we consider a curve here, and we consider its tangent vector at this point, now I could say, what is that tangent vector? I could rigorously define that. There's a lot, I've got a whole derivation here, which I choose not to go through for time. That's basically this tangent vector, all it is the directional derivative of this line here. How do I have this here? Yeah, so all this works is this vector, all it does, it works on functions to get this, you know, it's a magnitude against the derivative, right? So you end up with something like this. Partial x mu gives you this sort of tangent derivative, tangent vector. So this thing acts on functions, as I said before, and it maps functions in a abstract sense. So let's not get too confusing. Like, let's work here. So this surface here, right? The surface here, at this point we have loads of curves going through that, and we can actually define, of course, you know, we have many curves going through this, and we can just define, if we take 2 of them, for example, and get 2 of their vectors, like that, we can just already define a plane, right? Hello. Oh. So we can define, so once we have 2 vectors, we can then define, you know, we have a basis from those 2 vectors. There are processes to get them, right? And you can, from that basis, you can define this tangent space. So on a 2 manifold, it's rather easy. You end up with a plane. On a 3 manifold, you get another 3 manifold, 3 Euclidean space from it, and so on and so forth. So that is kind of the idea of what a tangent space is kind of trying to say, is like, it is a vector space that is defined at this point from all of the curves that come through this, right? So, yeah. So now this brings us on to our main point here. What is a Riemannian manifold? So a Riemannian metric on a manifold M is a smooth, symmetric, covariant two-tensor field, G, defined on the manifold M that is positive definite at each point. That is the definition of a Riemannian metric, and a Riemannian manifold is just a manifold that has such a metric, right? Surprisingly, every differentiable manifold is Riemannian. Now that is a rather, strong statement. Heck, like it's one of those wow. Like, it's not wow yet because you guys barely know what this two-tensor field thing is, right? So let me kind of describe the Riemannian metric. So two-tensor field is just a tensor that's defined at every single point, and basically what we're saying here is that on a manifold, or rather any differentiable manifold, you can define a positive definite metric, two-tensor field, symmetric, that has these properties. So it's smooth, so it's infinitely differentiable. It's symmetric, so that anything along the diagonal is kind of reflected, right? It's covariant, so it has two lower indices. So if we write it in a tensor notation, we could write it with two lower indices, and so on, basically. So let me just quickly define the Euclidean metric. So the Euclidean space has a metric. It's the metric is simply, its components are simply the Kronecker delta. And as we like to write this this is not a matrix, but I'm going to write it as a matrix so that you can see all of the components, right? Which in 3 space is just the identity matrix. So when these two are equal, they are 1. When they're different, they are 0. So that's what that is. But what is this metric thing, right? Well, in reality, it is the generalization of inner products. So if you recall from Professor Muscat's lecture, when we have two vectors with their components being contravariant, so that's called W, we have two vectors like this. If we were to find their inner product, so if I want their V, and for those of you who are a bit confused with this, inner product is the same thing as dot product. Like it's just kind of a bit more of a, fancy words, I guess, so to say. So this inner product thing, right? The way we would write it last time is like this. So we'd write our Kronecker delta with its components, and like this. So, and now, excuse my handwriting, but like that. Which, if you want to recall the way Professor Muscat showed us, like he gave us like a bit of a geometrical view of what tensors are. So we could write this tensor here. So lower is always one way. I'm going to give it to the right for an example. And upper is always to the left. And we're just plugging these things in like this. Right?
This is for base vectors, right?
Well, this is kind of, for the basis vectors, for Cartesian coordinates as well. So, yes? Yes, I can. Let me. So, inner product, is that better? Yeah. And we just write this like this, yeah? Cool. Yes, so this is just the specific inner product for Cartesian coordinates and so on. In fact, change of coordinates will change this thing here, and will actually, so we generalize here and we write a general 2 tensor rather than just the Kronecker delta. We write this G mu nu, and we get the inner product. So now that I've hopefully kind of wooed you into like what these metric things are and why they're important, it is a little bit fascinating that every differentiable manifold has a Riemannian metric. Now, let me show that. Well, as I'm not too familiar on the details, but I can give a little bit of an overview of what the proof entails. So if we consider a manifold, general manifold, a differentiable manifold, we can cover it by some finite chart, finite atlas rather, and we can get each of these parts into some set. Now, not to forget that each of these parts are locally Euclidean, so each thing here is a Euclidean space. And since it's Euclidean, it exerts the Euclidean metric. So we can define that for this specific chart, this sort of metric here. Then there's like some complicated way of summing these things up. And basically the idea is to stitch all of these Euclidean metrics together and solve and find this overall metric tensor for the entire manifold. So that's kind of how this, like just the surface level of how this proof works. So hopefully I've convinced you somewhat that every differentiable manifold is Riemannian. So a couple of things about the metric tensor. Of course, yes, it is just a representation of the Riemannian metric. And the Riemannian metric itself is a function that maps, so any two vectors in our tangent space onto a real number. And in fact, it is given by this inner product. So we can define this G of VW, we can define this as being G of VW like this, right? It has, you can define a bunch of useful properties from this. For example, the norm. The norm is like defined in the very usual way. It's just the square root of the inner product. We can define the angles. Like again, like if you were to see this in A level, you'd see this as a dot product here, right? So it's exactly the same definitions. And another thing is like two vectors are orthogonal if their inner product is 0. If their metric, Riemannian metric, is 0 in this case. So is that okay with everyone? Okay. Is there anything on the chat? No. Okay. So another thing we can define is length in a very usual way, right? So if we consider a curve, that is just so a curve is, remember, is just a mapping from some subset of R onto the manifold itself. So I mean, ideally an interval, right? Like, let's make it useful. And we can define this curve, as the integral between of this norm, the norm of the derivative of the curve, which is rather, it's just exactly taking what we've done in vector calculus and just putting the new, more general thing in there. So we've been talking about lengths, sizes and whatnot. But the next question we'd like to ask is this a metric space, right? Like, it kind of makes sense. We're talking about distances somehow, right? And yes, the answer is yes, frankly. And we can define this distance function here. So basically, we define this set of lengths of the curves between 2 points. So P and Q are points on the manifold. And if we have a curve, so it's a set of, we consider the set of curves, and then we just apply the length formula from the previous slide onto these curves, and we take the infimum. So we find the least distance between the two. And well, a couple of the points take a few. So a couple of the points take a few. Yeah, exactly. So yes, this is what I wanted to say. Most of the points are. So these three are rather simple to see, and this one takes a bit of work as usual from metric spaces. So, you know, the distance between 2 points is 0 if they're the same point, and you know the distance is positive definite. Symmetry holds. The triangle inequality is obviously always a bit tricky to solve with this. So, so yeah, this is. I mean, the way you'd work this out is just find the lengths. You know, you define different curves that go through these things, and then define their distance, and you'd actually eventually find this inequality somehow. So, from the chat, yes, let's see. Well, to answer your question, Luke, it's infimum because the book said so. Yeah, no, minimum, I guess. If we're talking about an infinite number of curves, there is an infinite number of possible lengths, right? So if we have 2 points here, right, we can think about lots of these different curves here. So yeah, I guess infimum does make sense because you can traverse the entire manifold like this, right, before you get to the other point. You just get an infinite number of these, or rather, more interestingly, is little perturbations of these things. I guess a minimum would be reached, but yeah, I guess there would be an example. Yeah, kind of like the topologist sine curve, I guess, with connected spaces and stuff like that. To be in one of those weird topology books, right? Yeah, is that? No worries. Aha, so yeah, you could define this sort of metric on this thing. And yes, so in fact, this makes it even more surprising, right? This previous fact that I stated. This thing here, every differentiable manifold has a Riemannian metric. Not only that, if every differentiable manifold has a Riemannian metric, then on the places where that metric is defined, you have a metric space. So this is like, wow, mind-blowing, right? You can define distances on any manifold that you can think of somehow. Now, obviously, this kind of helps. This kind of helps this last point here. Rather the second point, positive definiteness, is a thing to consider, right? We previously defined the manifold, the metric tensor, to be positive definite. So every element is positive definite. Pseudo-Riemannian manifolds, however, are not the case. So pseudo-Riemannian manifold, firstly, is one. So if I go to the definition, it's one where we have a non-degenerate two-tensor symmetric smooth field. Now, what is that? Yeah, that's a bit, wow, big words, right? So two-tensor, or some function like this, a symmetric two-tensor on a vector space, is said to be non-degenerate if for every non-zero vector there exists another vector in the vector space that is not orthogonal to it, so it doesn't give a zero. So it's non-degenerate if at every point you can find a vector. So it doesn't mean that the vector doesn't have an orthogonal point. It just means you can find a vector where this inner product is not zero, right? So these zeros do exist, but it's just we choose for every point that it's not there. So that's kind of the idea of what non-degeneracy. I mean, in math and physics, when we say something is degenerate, usually we mean that there's a zero. Degenerate eigenvalues are tend to be zero, right? Yeah, so we choose non-degenerate right here because we have non-degenerate here for this two tensor, right? So because we want this not to be zero. So yeah, pseudo Riemannian manifolds are just Riemannian manifolds with a metric tensor that is everywhere non-degenerate. So at every point in space, for all vectors in the tangent space, you can find a vector that is not orthogonal to that vector. So this kind of leads to some caveats, like, for an example, like the only difference between this and the Riemannian, the big difference anyway, is that it no longer allows positive definiteness, which is kind of the point. And actually, you can define a pair. You can find a pair called the signature, the metric signature, which defines how many negative eigenvalues and positive eigenvalues you have. So, in fact, this is something very common that you see in different textbooks adopt different signatures for when we're talking about specific manifolds, like the one we will see in a little bit. Now, I've done a lot of math, and I'd like to kind of reward it with some physics. And we're going to apply this stuff now. So back a long time ago anyway, Maxwell came up with his differential equations for electromagnetism. And he came up with this equation here, right? So the Laplacian of the electric field vector is equal to some constant. These are physical constants, mu and epsilon. Like if you've done some electricity, you might have seen these. And it's equal to that times the second derivative of time. Now this, I mean, if you've done any wave equations or anything, like this is just the wave equation, right? And this kind of gave some ideas as to, oh wait, is the speed of light constant? What? So like, because at the end of the day, the light is just pulses in electromagnetic waves, right? So this is the wave equation. It's just 1 over c squared there instead of the constants. So you can define those two constants, those electric constants, from the speed of light. Then you had Michelson and Morley. These two guys, they had this experiment because back then there was this idea that the speed of light was relative, and it would change because it would fluctuate through this material called the aether, which they conducted this experiment with some interferometer and stuff, where they basically disproved this theory, right? So they said, listen, oh no, this relativity, we must be wrong. I think I've got a mistake in my calculations. But then later on we just adopted this. Einstein saw this, adopted this, and said, oh yeah, great. So let's consider this to be the truth, that the speed of light is constant no matter on the reference frame. This leads to a lot of weird things, right? So let's imagine that I'm holding a light source here, right? So if I drop it here, you see it drops straight down. So we've got a light source bouncing up and down here. But if I start moving like this, the way you're seeing my pen go up and down is in some sort of sinusoidal fashion, compared to me, where I'm seeing it go up and down, right? Does that make sense? So that leads to a lot of weird stuff, right? Because if we have, let me make some space. If we have, so for me, it's just going up and down like this, right? But for you guys, you're seeing it bounce as if it were bouncing off mirrors like this. The path is much longer for you. Like, what the hell? This path here is obviously much longer than this path here, up and down. So, this idea of constant speed leads to a lot of weird ideas of like, oh, when I'm moving, time slows down for me and distances get longer, something like that. Anyway, it might be the other way around. All because we're getting this idea of the speed of light to be constant, right? Well, there was a lot of work on this idea, right? And eventually, this guy, a lot of people, a lot of, popular names like Minkowski, David Hilbert even pitched in. There were a lot of people working on this idea in math because, you'd need a formal idea of what these things are. They kind of worked on these things, and they came up with these things called Lorenz Transformations, which makes you see what I see in my reference frame if you're in a different reference frame, and so on and so forth. And eventually, it came up with this metric for Euclidean space. Now, obviously, this is a pseudo Riemannian metric because of this boy right here, this -1. Like that basically is there because of the time component, right? And as I said before, there's this metric signature where here we can see this. In this case, it would be 1, 3. We'd have 1 negative and 3 positive, which typically is written like this, right, with a bunch of pluses. Different books will use different metrics. As long as there's one different, it doesn't really matter. As long as, so you could have a +1 here and minuses all over here, right? So that's the idea of the Minkowski metric, yeah? So this thing encodes all of special relativity. So this idea here, and transformations with this. Now, in what was it, 1910, 1915, in those years, Einstein started working on his theory of gravitation because he just didn't like how Newton's worked, and it really didn't gel together with the ideas of special relativity. And he was working in his patent office, and he had this, the happiest idea of his life: a guy jumping out of a building. That's the story. Anyways, the idea was that he'd see, the guy would see the ground come up to him, and he would see light work differently, and so on and so forth. And that kind of all gave rise to the equivalence principle. Now, the equivalence principle is a very big thing. It's a thing in Newtonian physics too, but well, a weaker version. This is just the strong version that Einstein came up with. The idea is that the mass, so when you have, so remember, you should know this equation. This is Newton's second law, right? And Newton came up with the idea of, well, his theory of gravity had this thing, right? So the force due to gravity is because of this equation. So you have the mass of the object and the mass of the two objects, basically. And here, this is the inertial mass, needs some force to be accelerated, is the idea. And typically, you would solve this like this, right? You'd get your MA here. This would need a vector, I guess, or unit vector like that, right? Just to make it simple, let's get rid of the unit vectors. And typically, you would want to track the motion of a single object, and you would use the same mass here and here. That is kind of saying, oh, the inertial mass and the gravitational mass are both one and the same thing. So that's kind of a weaker version of the equivalence principle, but here we would like to use an even stronger one. And it basically states that in small regions of space-time, the laws of physics reduce to those of special relativity. And it is impossible to detect the existence of gravitational fields by means of local experiment. To me, this screams manifolds. This screams manifolds. Because if we let's consider Earth as a 2-manifold, as we do, right? Or, well, a 3-manifold, I guess. Well, no, 4, because we live in space-time, right? We go through time. So if we have Earth, right, at a local point in space, that is homeomorphic to r to the 4. I'm going to write it as, a plane here, but, So at any point in space-time, it's homeomorphic to r to the 4 locally. in some neighborhood. And all this says is that if it's, though locally it is special relativity, then this carries the Minkowski metric. And we use the Minkowski metric locally. You know, all of this then eventually came up to a lot of, you know, study and stuff, and you know, ideas on curvature and all of that, which I just simply don't have time to get into, which, you know, eventually came up with this equation, right? So this equation is like the crux of general relativity, right? It's like the big thing that says, okay, on this left side here we have our differential geometry stuff. Here, this G, we already know what it is. It's the metric tensor. This R and, well, these two R's. So R, this is something called the Richie Tensor. All it is a combination of derivatives and stuff of the G, of the metric tensor. And this R here is simply just the trace of this R. So it's on this left-hand side, it's all stuff to do with the geometry of the space-time. On the right-hand side here, we have 8 pi t mu nu. Now 8 pi is there for you know, conventional reasons, basically, so that at low scales or whatever we can get back Newton's physics. The t mu nu, however, is something of utmost importance, something called the stress energy momentum tensor. All it is, it's a two tensor. It's covariant, obviously, because I'm using lower indices. All it is a description of the stress, energy, and momentum, as the name says. You can think of it more as a description of the matter content of your space-time. So, you know, there's a lovely quote by Wheeler that says, you know, space-time tells matter how to move, and matter tells space-time how to curve. And that's kind of the big idea with this equation, and it's absolutely amazing. This is, you know, partial differential equations to solve for. So, you know, you can get loads of different metrics and figure out what the matter content would be, and you could put a matter content there and then solve for the metric tensor, which is a very difficult thing to do. But it's been done, and you know, that sort of thing has been done, and from that we get discoveries like black holes and all of this, you know, just came straight out of the theory. So with that, I'd like to conclude there. If you have any questions, please feel free to ask me. Thank you. Any questions? Any questions in chat, maybe? Tell me, Luke. Another pedantic question.
In the meanwhile, as I thought about it, by the way, what I said about basis vectors was that for a moment I found your notation a bit like confusing, because I haven't seen it in a while. You must intend the V and the W are going to give you their own side, right? So it won't be ones and zeros everywhere.
Yeah,
there
exactly.
will be the contributions from V and W.
Mm-hmm.
Right, so Anka forse għamil ħatma ħadem bjom daw the Kronecker delta is kind of giving shape to this matrix. The Kronecker delta is kind of saying which terms from these sum are going to contribute to the inner product. Of AM1, ħajkun hemm contribution, for AM0 mhux ħajkun hemm contribution. When the indices match, you're going to have contribution. When they're not going to match, you're not going to have contribution. And it's not just going to be 1 and 0. The 1 and 0 are controlling this contribution, and that where it's not 1 and 0 is coming from the V and the W. So one, I wanted to point it out as I messed up there, but also because maybe it makes it a bit more tangible for us.
Yes. Brilliant. Let's see what Luke said. Can you explain more a bit about non-degenerate vector metrics? Yes. Yes, so I mean the basic idea is, oops. So, right, a non-degenerate metric basically has the, I mean, to me, all they are is just there's just a metric tensor that is not positive definite, but still has all of the same nice properties like symmetry and its covariantness and stuff. So the way I understand it is that basically at every point in space, we can define, we can find at every vector in the tangent space, we can find another vector that is not orthogonal. So we can find, so if we have a tangent space like this, we can find a vector like, two vectors like that, basically. For any vector like that, we can find one like that. So that's, does that kind of answer your question, Luke? Brilliant. Okay. Any other questions?
I would point out another thing based upon a question one made, and also like so the way that you were describing vectors is not maybe the same way I think of vectors. You think vectors are things that act on functions. So
Yes.
I think of vectors as functions also. So Aliyah vectors are functions from the field to the vector space. So if you have, say, the vector space is R and R to the n, for example, all the vector is a function from R to R to the n.
Yes.
Then a dual vector is the opposite of that.
Exactly.
Function from R to the n to R.
Yes.
So when one asks sort of are these functions though, I would say they're all functions. But
Yes.
وقال كمان sense الحاجة عاش dual vectors ما vectors وقال. So my search on the dual vectors so my functions so
Yes, says that. I mean, at the end of the day, the vector space itself is dual to the dual space, right?
Exactly.
So you can think of them both as functions in some sense.
So I just wanted to point that out.
Yes.
For the sake of
In reality, it's just we take one of them as vectors out of convention, right? We could think of them both as duals of each other at the end of the day. So, is that it? So thank you very much for attending. Just being my MMS guy now. Next week, Jake here is going to.
pitch my talk really quick.
Yeah, come here and pitch your talk. Yeah.
I think I'll just go you start your smiling. Yeah, so next week from 5 to 7, I'm giving a talk in the first hour, I think, and Luke Collins is giving a talk in the second one. I'm not too sure what Luke is talking about, but I imagine it's going to be like number theory related. He can comment in chat if what I said doesn't make sense, and we'll arrange it. But what I'm talking about is, I'm talking about applications of differential geometry to quantum information. And in particularly, I'll be explaining the Solovay-Kitaev theorem, which is really essential for making sure that we can do universal quantum computation in such a way which is pragmatic. So it's about how many gates do we need to be able to do any type of quantum algorithm. But it turns out that it's a really cool and funky differential geometry result on the group of unitary operators SU2 in Somma. And yeah, you'll find out more about it next week. Thank you again, Ethan. Oh yeah, ciao.